right, shall we get started? Okay, so today, 3 things I'd like to talk about. The most important thing I think today would be we're going to discuss projects a little bit, and I'm going to give some guidelines on expectations for what these presentations are going to be like. But first, while I have everybody in the room, I was just wondering if there's any feedback, or does anybody have anything to talk about the exam? I personally thought people did reasonably well. I mean, the exam curve ended up exactly where we like to hit. We like to hit 70%. I tell everybody we do not want perfect scores on the exams. And after the regrade requests, which please get them in by 5 p.m. on Friday. It was a long exam. I'm sure there are plenty of things that could get regraded. It was all done in one sitting by the TAs, so thank you very much to them for doing that. Yeah, I mean, it's going to come out exactly where we like. There was almost a high score. I mean, there was almost a perfect score, and I think people were answering a lot of the questions pretty well. So is there anything that we need to, and I'm more than welcome to come talk to me or to Professor Bryant or anybody else in office hours if you are still confused by any of the problems. Just because there's no deal or no more grading on that kind of stuff doesn't mean we can't keep talking about it. So we have all next week to talk about it. Any other questions? Everybody cool?
Comments?
Sorry? The floor is yours.
Well, maybe comment on a comparison of exam 1 to exam 2.
Sure, yeah.
It's a bit better structured than exam 1.
Okay.
Exam 1
hear that?
was more arduous than exam 2.
Usually in this class, for whatever reason, and it's not intentional at all, it's the students do feel that exam 2 is easier. And I think people do feel that exam 2 is easier because you've just had more practice with my question answering asking style at that point, I think. Yeah, might be the case. That might be true. But yeah, in general, the trend was similar this year, is that people felt a little bit better about themselves after exam 2. Anything else? Nothing else? Okay. So a few announcements is your final project presentations are on May 9th, so a week from Monday. So we're about 10 days away from that. The way this is going to work, hey everybody. The way this is going to work is that we have an exam slot. Our normal final exam slot is 8:30. Unfortunately, 8:30 to 11:30 on that day. Luckily, it's the last or second to last day, so hopefully you're not super burdened with other exams. With so many of you in the class, obviously everybody cannot present in that window. So the way this works is that everybody will do a 6 to 7 minute presentation on that day. Some students or some of the projects will be selected the day before to present during the exam slot. That will be our official parallelism competition finals. We have some judges coming in from NVIDIA, from Intel, and from Google. One of the judges, for example, is the creator of ISPC, which he knows some of this stuff. Or the co-creator of ISPC. He's also one of the guy that designed the first shading language at NVIDIA. He's actually our Google judge, but he wasn't NVIDIA at the time. So there'll be some folks that know a lot. I've heard that Apple will be present because they just want to see your presentations, even though they're not participating in the judging. And we'll see what prizes we can drum up out of industry. So I definitely know we'll have a Titan X. I definitely know we'll have a pretty cool drone.
Is a Titan X one of the prizes?
Yeah. So it's one of the prizes. I definitely have an Apple Watch. From last generation, I'm sorry, not the new one. Sorry. And I have a Titan X GPU. Well, I have promised Titan X GPU. I should be a little careful. And we have a drone from a hedge fund that liked what you're doing here. And then we're trying to get a few more, but we'll see. So the way it works is that the competition is not really it's just for fun. It has nothing to do with your grade. Your presentations are part of your grade, meaning I will grade your presentation as part of your project. But who wins the competition, that's just kind of for fun. It means some people are going to end up walking away with some gear and some people won't, but it does not affect your grade at all. Many times there are people that place in the competition because the judges like the presentation, and it turns out they don't get the best grade because it happened to not be a very technically hard project or something like that. So Grading is between you and me. The competition is everybody's going to have a bunch of food and eat food and watch some cool presentations and have fun. Okay? Yes?
So when do you have to get the projects to a point where like they can be judged to be?
The way it works is that we try and late bind this as much as possible because I know the last 72 hours of a project, things change dramatically. So typically, for us to be able to scan through all the projects and help the judges narrow down to about 20, because really that's just the amount of time that we have, we pretty much say that around noon on Saturday, your web page better be in a state where if someone of us looks at it, we can assess your project's progress and make a good assessment of what's going to be possible on Monday. So about noon on Saturday is the cutoff date.
Do you mean this Saturday?
No, noon on the Saturday the 7th, right? Yeah, Saturday the 7th. Okay. And then the project reports are due at midnight that night because sometimes people want a little bit of extra time to write things up. Okay, so we did the discussion. We talked about final projects. So the parallelism competition, so to speak, is just for fun. Everybody, you should plan to have a 6-minute talk with 2 additional minutes for either the course staff or the judges to ask you questions. And this is just for reference. I want to make sure that you start, your presentation starts with the names of everybody so the judges can write down who it was. Otherwise, we're like, hey, we really like that project, but we can't remember who it was. And the assumption is that you'll just print off, you'll present off your own laptop here, or if you want to give your slides to me or to one of the TAs in advance, we'll have one laptop that coalesces a bunch of the slides, just to keep things going on. So the thing that should jump out at you on this slide is that you've been working for 5 to 6 weeks on a project, and you've got 6 minutes to talk about it, which is a tough sell. It's a tough thing to do, which means this is why I want to give some project presentation tips. And this, I hope, will be helpful to you in your projects. I hope it will help you to you after this class. And for God's sake, it's really helpful to me because I got to listen to a lot of projects. So hopefully this will be useful. So isn't there a class in this? Aren't you required to take a class on technical communication or something like that? Okay. All CS majors are, right? Yes, but not easy. Okay. Well, so maybe some of this stuff you might have already had some of this stuff. But so why am I requiring you to give a good talk? Or not give a good talk. Why am I requiring you to give an oral presentation? Why not a poster? Why not just hand in a write-up? This is by design. Being able to speak clearly about a technical topic is a pretty useful skill beyond 418. So I find that that's a much more useful skill to you than making a poster, because that rarely happens when you work at Google. Your boss doesn't say, go make me a poster. Your boss says, I want to meet with you for 5 minutes. Can you make an argument on why your lock-free linked list is the right way we should go? And so being able to deliver a good talk is incredibly valuable to you. And the reason why it's valuable to you is that it tends to be the people that there are many people that do really good work in the world. But there are fewer people that can communicate their good work effectively. And the inability to communicate your good work effectively diminishes the impact that your work may have. Because other people are more likely to remember what you did and maybe build on the work later. Or maybe it's not applicable right now, but a year later, that boss comes back and says, hey, remember when you did that? I really understood what you did, and now we really need it. If you're in a conference setting or you're here, others are more likely to come up to you after the talk. For example, maybe our guest judges or something like that. And in general, we sit through a lot of bad talks in the world. and people respond to somebody giving a good lecture or to giving a good presentation, because people just really like that. And the number of times that I've seen a student give a good talk and somebody comes up to them afterwards and says, hey man, that was a really great talk. I really enjoyed that. Or I actually understood what you were doing, unlike everything else at this conference. Are you looking for a job anytime soon? Those are the types of things that happen when you can give a good talk. So, the number one priority in you giving your project presentations should be to be clear rather than comprehensive. You have done 6 weeks worth of work. There is no way that you can talk about 6 weeks worth of work in 6 minutes. So the goal should not be to get everything in there. Your goal should be to have everything that you say be more or less understood by most of us in this room. So I like to live by the philosophy of clarity is much more important than getting a lot of stuff in. And this is going to be a lot harder than it actually seems. So here are some tips. So my first tip is the hardest part, is you've got to figure out how to put yourself in the audience's shoes. So as instructors up here, whether we're writing an exam or giving a lecture, we're constantly thinking, okay, what are the students going to think about this? If I was a student and I'd never seen anything like this before, is this going to make any sense at all? And as a professor, we kind of do this every year, and we start to get a little bit better at it. And we fail all the time, but we're a little bit better about it. And the check that you should just say is, look, say what you just put on your slide out loud. Right? Like, this is some homomorphic embedding of blah, right? And then ask yourself, are people going to actually understand what I just said if they hadn't been working on this project for the last six weeks? And if you don't think that people are going to understand what you're saying, you need to take that sentence out or think of something else to say. Because saying things that people don't understand is just wasting everybody's time. So in this class, you can assume that everybody in the audience, all of you, have taken this class, right? You can assume that the staff, hopefully, and the judges, for sure, understand parallel programming. We know what SIMD processing is. We know that workload balance is a problem and things like that. What we don't know is we know little to nothing about the particular project that you chose to do. What the application is, why is it interesting, what's its hard. And so the judges and myself, when I'm trying to grade your projects, is we are trying to figure out essentially the most interesting thing that you found out or accomplished in this 6 weeks. And interesting should be defined by you. So in working on the project, you should be like, wow, this turned out to be really hard, and it was really interesting how we solved this problem. Or I never would have thought that the CPU was going to beat the GPU on this task. That's interesting. I'll make that the hallmark of my results. So choosing what is interesting is probably one of the most important things you can do in a talk, which leads me to point 2, which is pick actually a focus. And the best tip that somebody ever gave me in giving talks was figure out what you want to say and then just say it. Don't say anything else. So a good speaking philosophy is every sentence matters in a talk. So if you put a sentence on a slide, or if you say a sentence out loud, you should ask yourself, back to the focus, what is the point that I'm trying to make here? And did the sentence that I just say make the point? And if it doesn't, take it out because it wasn't particularly helpful. If you can do a one-sentence talk, all the better for you. So in this class, your projects are shockingly different, right? Some are applications projects, some are analysis projects, some are systems design projects. And so different projects should stress different things. For example, it might be best to just show a flashy demo, which means like the hard and interesting part of our project is that we just wrote a ton of code and we got it to all work, right? And it's proof by I can show you a demo of it working. Right? That would be the best thing to show. Other projects would be, this was a very narrow, I was interested in one algorithm or one application, and here's the sequence of optimizations that I did. And let me show you how everyone mattered. Maybe a sequence of graphs or something like that. Other projects might be like, okay, I did the same thing. I did it on multiple platforms. I wanted to figure out which target was the best, and I figured it out. So let me explain that to you. So your job is not to explain actually what you did. Your job is to explain what you think the judges or me should actually know. Because you spent 6 weeks on this. I want to know what you learned so I don't have to repeat those 6 weeks if I ever wanted to do the same thing. That is your job, is to figure out what's important and only say that. So let me give you an example of something to never, ever, ever do, which violates everything I just said. And many classes tell you to do this. This is slide 1 of so many talks that I see. Now, in a 6-minute talk, you probably won't do this. But this particular speaker is telling me that he is going to introduce his work. He's then going to tell me about related work. He's going to describe his work, and he will conclude at some point during the talk. which is not really something that I'm surprised by, right? So he just wasted a good bit of his introduction not thinking. Someone told him, or her, I don't know who made this slide, you always make a roadmap. And if the roadmap is obvious, why is there a roadmap at all? So this is a good one example that I like to use, because every student often just puts up okay, we're gonna do this, and we're gonna do this, and we're gonna do this, right? I actually had a roadmap at the beginning of this slide, the beginning of this lecture, which says we're gonna talk about the exam, we're gonna talk about this and that. That's a very different case, right? Like, we don't really know what we're talking about today. But telling me the basics of a talk is not something that I need to know. Okay, so next, oops. So if the number one principle is figure out what you want to say and only say that, take everything else out that's not making your point, the number two principle, even though we're on number three, is the audience prefers not to think much. So this may not make a lot of sense, but the audience has a finite supply of mental effort when they're listening to you giving a technical talk. And we push that in an hour-and-a-half lecture, actually. But the audience does not want to burn their mental effort thinking about things that you can just tell them. They want to burn their mental effort, like they don't want to burn their time trying to figure out what the x-axis is. They don't want to burn their time trying to figure out what that term is, and this and that. They want to be thinking about analysis. They want to be saying, what are the potential problems with this project? Is their evaluation sound? Is it related to what I am doing, because this might be useful to me in my group at Apple or whatnot? Or is this a good platform for this workload? Like, they did this application, I think I understand it from their talk, but they chose a CPU, and this is like a perfect GPU app. Have they just missed one of the key principles of this course? So you want people thinking about this kind of stuff in your talk, not what's that x-axis again? And I'm going to come back to that in a second. Okay, so now we're kind of getting into, we have our philosophy. Now we're going to get into sort of some of the mechanics. So you need to remember that nobody understands the problem that you're working on. So you cannot just describe it by name. You can't just say, I'm implementing a deep neural network on the MNIST dataset. That won't mean anything to people that haven't worked on your project. So you need to establish and describe your work in computer science terms, because that's what we all know. And computer science terms are inputs and outputs, and operations that get me from inputs to outputs. And then the last part of the problem is, what are the constraints? We need to take these inputs to those outputs subject to some constraints. So given these inputs, we wish to generate these outputs. And the problem is actually interesting because I have some constraints. My constraints might be the output should have these properties. Or the constraints might be the algorithm's got to run in real time, because if I'm doing computer vision on a robot and it doesn't run in real time, that's not a particularly useful solution. It needs to interoperate with this existing library that we can't change. So even though you might think, oh, we should do this, we can't do that because we are constrained. Or maybe we're constrained because it's an interface, because I'm doing my own implementation of GraphLab, and GraphLab can't be changed. So, so those are good examples of algorithm constraints. Examples of systems constraints might be something like, well, I did a Python to GPU conversion, and, well, I didn't do all of Python, because it doesn't really matter to me that I needed all of Python. Here's the subset that I used. Or my goal is to get about 90% of the performance of me doing it by hand, but I want to use my fancy system to help me. So those are examples of goals and constraints. So if you tell me the goals and constraints and the inputs and the outputs, now I can start being like, okay, I wonder how I would solve that problem. I now know the problem, basically. So now I'm actually set up to start thinking. You also need to tell me why solving the problem with those constraints is actually hard. Because if I'm thinking, well, that seems really easy, seems like you just throw a parallel for all loop around that. But there's probably something in your project which made it a 5-week project. That's the important information that you should tell all of us. So in this example, it might be, why is this problem useful for optimization? Or why is this the right problem to solve? And why is it hard? What turned out to be the hardest part of the project? This may involve describing the workload, but that just means that the part of the workload or the algorithm that you tell me about is only the relevant part to the thing that was interesting, and so on and so on. Okay, any questions so far? No? Okay. So let's talk a little bit more about, now we know, I've given you some tips on how we set up a problem. Inputs, outputs, constraints, goals. Why is making the inputs go to the outputs subject to those constraints actually challenging? Then the question is, what did you do? How did you actually solve that problem? And as I've stressed a couple of times in this class, I like to describe systems by describing state. What are the things? We have pixels, and we're turning them to more pixels. We have training data, and we're using it to train a classifier. We have a mesh, and we're trying to compute the value of fields on the mesh. So that's the state. And then there's the question of the verbs. What are the operations on the state? Which should lend itself to a very easy diagram. State, boxes. Verbs, operations, arrows between boxes, taking state to more state. Tip 6. Surprises in a talk are almost always bad. And what I mean by that is that this is not a creative writing class. Surprises are very good in storytelling and in creative writing classes. Surprises in a technical talk are not very good. So if you don't have a sense of where I am going, I'm doing something wrong. And what I mean by surprises are almost always bad is you need to tell me where you are going before you actually tell me what you did. Or another way to say that is tell me why you're telling me what you're telling me before you actually tell me something. Right? So this is, yeah. The outline, it's completely not interesting to tell me that you're going to conclude. This does not conflict with the principle of only say what matters. The outline is trying to get at this without saying the important stuff. So let me give you some examples. So in this talk, I decided to actually start by not giving you talk tips. I decided to give you some suggestions on why it might be valuable to hear the talk tips. So at least someone's saying, well, I know why I'm listening to this. I may disagree with the value, but at least he made an argument. So surprises are always bad, or give why before what, is completely consistent with the audience does not want to think. The audience does not want to think about why I am telling you something. The audience wants to think about whether or not what I am telling you is actually consistent with why I'm telling you that. So you're constantly checking about, okay, is this a good tip? Because if this is not a good tip, I don't know why I'm listening to it. So it really helps the listener because the listener can say, okay, the following part of the talk are going to be technical details about the algorithm. And so I know why we're talking about this. And if I happen to get lost, that's okay because I can come back to the talk later. So why gives the listener context for understanding how the parts of the talk relate? So why is the speaker now introducing a new optimization approach? Well, it's because our performance wasn't very good. You should always be able to answer that question for yourself when you're listening to a talk. So examples might be, before I tell you what I did, we first need to establish some terminology. Why am I telling this person about what a mesh is, or what vertices on the mesh is, or what the representation of the data structure is? You need to tell me why you're about to tell me this. Another example would be, even though I just told you the solution to X, we still haven't solved the whole problem because there's this other part of the problem over here. And then you're like, oh, okay, that's what he's going to start telling me about. And like, now that we have defined a cost metric, we need a mechanism, we need an algorithm to minimize it. So, okay, I understand the cost metric. Well, how do we minimize that cost? Oh, he's about to tell me. In the results section, I tell you what you should be thinking about, such as key questions to ask about approach are. And you as a listener go, thank God, because I didn't want to think about that. Yeah, let me go see if the damn graphs actually answer those questions. So I'm putting you in position to analyze my talk, not interpret my talk. Because the listener says, these are the questions that we should be thinking about in the evaluation. And you're like, you just wake up at that point. You're like, oh, I missed the whole method section. Thanks, those are really good questions. Let's see if you can at least answer those, right? So it gives you the ability as a listener to follow the talk. If you listen to nothing else that I say, it's this slide. If you listen to nothing else that I say, it's this slide. Remember, the audience does not want to think. So if I put a graph or a figure, I will explain it to you like you are a 5-year-old. Seriously. You might know what this picture is, especially if you came to the last lecture. But if I put this up in a talk, like in my lecture last time, I am remiss if I don't explain it to you. So here was my example voiceover when I gave this in a talk. So this happened to be a graphics talk. We were talking about figuring out what pixels are under a triangle. And so I said, look, here I'm showing you a pixel grid in gray. You probably could have ascertained that, given the talk, but I'm going to tell it to you anyway. I'm going to show you the location of 4 sample points within every pixel. And there's a triangle in white, and the sample points falling within the triangle are colored red, which most of you could have figured that out. But the point that I said that means that your eyes are going to all the visual elements of the figure and following along to see if you're understanding. Because you're looking at that, you're like, yeah, those points are inside the triangle. Like, I'm following this talk. I'm with this, right? What? Exactly. But that's really, really important. And if I use color, I'm using color for a reason. The reason why I use gray and black in all of my slides is because if I use color, it's because you're probably thinking it's important the minute I use color. So let me give you another example. It's a little bit more complicated slide. But you probably know nothing about this paper. But the point here is I can lead you through all of the important details. Here, last slide I showed you one triangle. Here there are 2 triangles on the same pixel grid. And I'm coloring the pixels according to the number of triangles that they fall underneath. And then comes the key word here, as you can see. And if people say this next week, that's perfectly fine. We might laugh because of the slide. But it is, as you can see, the pixels that are colored light blue fall underneath 2 triangles, which is actually the whole point of this particular paper. But I'm pointing out the salient part of the diagram. Here I'm showing you 2 triangles. I'm coloring the pixels according to the number of triangles that overlap every pixel. And as you can see, pixels at the boundary between 2 triangles happen to get overlapped twice. In this particular talk, that happened to be extra redundant computation, which is why that's a salient point. But again, it's like now the reader's like, yeah, I can see that. I'm totally following this talk. And that holds true for any graph as well. Any graph, this should be the easiest thing to present in the world, because you can take a step back, you can relax, you don't have to have anything scripted, and you just explain the graph for the listener. Hey, look, there's an x-axis. The x-axis corresponds to the area of triangles, the size of the triangles on screen. The y-axis corresponds to the thing that we're trying to measure. In this case, it's shading computations per pixel. And why am I showing you this graph? Well, because as you can see, there's a lot more work being done when the triangles are small. And as you can see, the red line is better than the yellow line throughout all of the triangle sizes. That's the level at which you want to explain a graph to some person. You don't want to say, and it's better. Because people have never seen this graph before, it will take them 30 seconds to get oriented if you don't tell them anything. You orient the listener for them. And then, exactly. And in this slide, I actually said, I might start with here's what this graph is going to show you in terms of here's a why before a what. So in this case, I might say, this is a graph that's showing the number of overlap computations as the triangle size changes. Okay. So there's something interesting about this slide. Does anybody notice anything about this slide? Specifically the title. It's the result. What does the title not say? It does not say results. Because the title, you only get 1 point per slide. Because I can't make multiple points on the slide. I'm going to click if I'm going to make another point. And the point is the title of the slide. And that goes back to, you don't want the person to the listener to be trying to figure out what's important here. So if the point is always the title of the slide, after I explain the slide to you, and then I say, and if I'm taking a while to explain it, you always have what the point of the whole slide is up top. And you can constantly be checking whether or not this graph convinces you that that point is true. And in this case, the point is algorithm 1, the yellow line, reduces the total amount of work compared to algorithm 2, which is the red line. That is the point of this slide. Yes?
Do you think it's a good idea to prepend these couple of results slides with each slide that just says a result?
No, I think you want to put it right on the data because you want the user's eyes to go back and forth. Because they're always saying, am I following this talk? Merging, does this algorithm reduce the total amount of work? Well, yeah, it does. I see it on the graph, right? So I'm following the talk. I'm happy. Okay, yeah.
The question was, prior to starting to talk about results, is it okay to just have a slide with the word results?
Yeah.
Oh, yeah, I think I might have taken that one out. Let me see. I have a long version of this. One of the things that I love is section slides to completely delineate talks, such as that. Because this is why before what. This is saying, now we're going to talk about presentation tips. If you missed the whole last 10 minutes, this is a good time to wake up and we can re-engage and we're starting from scratch. It's also a good time when you're a speaker. Now, this won't matter in a 6-minute talk. But this is a good time as a speaker. You can just chill out. You can take a drink of water. You're like, now we're going to talk about some presentation tips. It's actually a really good way for you to break up your talk into, okay. And so here are some examples, the details don't matter, of slides from research talks by my students. And if you look at the titles, you can basically just read the talk off of the titles. It's like an abstract for the talk. Yeah, and again, it's give the listener context. Let me see if I'm understanding what he's supposed to say here. Yeah, I mean, that graph makes that point. It seems reasonable. Seems reasonable. Here are some examples of bad result slides. I have no idea what any of these slides are trying to say, right? The point, either I have to ascertain it myself from this table of numbers, or I have to listen to what the speaker is saying. And if I ever forget the main point, because the speaker might spend a minute on this slide, I'm done, right? So again, wasted opportunity to make a point. Wasted opportunity to make a point. You're telling the listener something that they already know. And so the corollary to this, basically, is if you just read the slide titles all the way through, that basically is a 1-minute version of your talk. If you just stand up and say, algorithm B reduces the amount of work, happens to work better in this situation, and so on and so on. Those are all the points of the slides. And some more good slide titles. And this applies to both results and both results and diagrams. Okay, so this is specific to your talks. Provide evidence that you've done a good job. So what does that mean? Well, it's going to really matter. It depends on your project. And really, by a good job, I mean you have successfully applied principles learned in this course to a problem of your choosing. It should not be the case if you present and a TA or a staff member or somebody says, you know, like, your algorithm seems like it's a really poor choice for this computer. And so, like, your results don't seem to mean very much because, like, your problem size is way too small. That would be not successfully applying the results from this course. So your job is to tell me what's important and to give me some evidence in some graph that you've done a good job. And by a good job means there's not a trivially obvious thing that someone who has taken this class would say, yeah, I wouldn't do it that way, I would do it this way. So examples might be, we worked really hard and we read this paper. Our whole project was just implementing the paper. And our implementation is, you know, within 10%, within 20% or something like that, within 2x of this published thing. So, you know, that's probably pretty good, right? Or we profiled, and we know that we're running within 80% of peak on the machine that we care about. So it's pretty much compute bound at that point. And so we're doing a great job. And be careful. Every year we see students saying, here's my single-threaded C code, single-threaded written in Python or whatever. I spent 6 weeks moving it to CUDA. The GPU clearly is 300 times faster than the CPU. And I'll ask those students questions like, is this a GPU benefit, or is it because you spent a lot of time making your code better when you move to that platform? And if they say, no, that's, you know, like it's GPU has way more parallelism, that's why it's 300x faster, that's not a good answer, right? That's not applying the principles of this course. And then the last is pretty obvious. It's a 6-minute presentation, which means in 30 minutes you can practice it like 4 times, right? So especially because we need to stay on time, because we were listening to like 60 presentations that day. To be smooth, you know, to make every sentence matter, you're going to have to practice it a couple times. And in 6 minutes, if you like are struggling with what to say, you're going to lose time. So just running through a few practices the night before is a perfectly reasonable thing to do. And I recommend grabbing a friend to make yourself a little bit nervous to practice in front of somebody else. It's a very useful thing to do. Okay, so those are my unsolicited random tips. Any questions? Yes?
If it's a partner presentation?
Both people need to speak, because it is part of your grade, but that's usually fine. Anything else? No slide that has a title that says results, please. Yes?
We're doing something that's not as straightforward as like CUDA or whatever. How much time can we spend explaining the concept that we're on?
You have 6 minutes. And your grade is going to be dependent on me reading your write-up and me listening to your presentation.
You also want to like present the results and stuff like that?
Yes. It's hard. This is actually a 6-minute talk is really hard. It's really hard, which is why we're getting practice doing it. But you know, you walk into Y Combinator, they're not going to say, it's fine, take 45 minutes, right? Okay. Any other questions? Okay, cool. All right, so let's wrap up. So the point of this course, and hopefully you have gotten something out of it, is that for the foreseeable future, it is true that the only way that we are going to gain more performance is through a combination of parallelism and specialization of our computing resources. There are alternative, very researchy alternatives that people are exploring out on the horizon, but at least for the first decade or so of your careers, it's going to be parallelism and specialization. And I put a couple of modern processors up there to just show that like we have multi-core CPUs, we have lots of core CPUs, we have integrated CPUs and GPUs, we have crazy high-end GPUs, we have mobile processors which involve GPUs and CPUs and ASICs for media, and increasingly there's increasing interest in more exotic fabrics like reconfigurable logic and FPGAs. And today's software, proof by assignment 1, proof by all of your assignments, is surprisingly inefficient on these machines. And they are tricky to program, but there's a lot of flops. There's a lot of operations that are on the table that we don't have today. And extracting this performance will have a notable impact on what applications are even possible in the next decade. 10x performance, 100x performance, 1000x performance totally is a regime change in what is possible on a mobile device or on an embedded device or an IoT or a smart or a self-driving car. So given the state of affairs today, knowing the things in this class are just going to be very important to getting that performance. And to me, it's very exciting, like sort of what the next 5 to 10 years people will be developing. And they're all extremely performance-oriented applications, whether that be autonomous vehicles, whether it be always-on audio processing, whether it be whether or not AR and VR really catches on, because those are really expensive. We have all the IoT devices, and these are big ones compared to other IoT devices. Energy efficiency, cramming the most compute into these devices at low energy is going to be super, super important. And in this, in this class, we've addressed these issues in terms of identifying parallelism, taking a look at an application, figuring out where its dependencies are, figuring out what can be parallelized, and then most importantly, most of the time that we spent, and I would really like you to take this away, is not identifying parallelism in most cases. It has been managing or scheduling that parallelism. And that has been achieving good workload balance. It's been overcoming communication overheads, exploiting or taking advantage of locality, choosing what processor should be the processor that runs different things. Those are the things that are really, really hard. Not necessarily how do we just throw a for-all loop around everything. So this class could almost be called managing state and synchronizing parallelism. And we've addressed these issues at a whole bunch of different scales, meaning that they appear at all levels of computing today. Okay, so a few more things is I'd first of all very much like to thank my TAs, who I don't think many of them are here, but we'll put it on record. I think they worked very, very hard. You will interact with them on your regrades still for a while. And I do encourage all of you on projects, do not be shy about asking for help. I know you have project checkpoints that some of them haven't been responded to. We'll keep, just pull rather than wait. So we'd love to work with you throughout the next 10 days. People that are going to bother us a whole lot are going to get more service, basically. Speaking of TAs, this class is being offered in the fall, not just the spring next year. So we have an immense need for TAs. As you can imagine, this class is actually quite labor intensive with some of the stuff that we try and do. So it depends on having really good TAs. And so you should reach out to Professor Railing or Todd Mowry, who will be teaching the course in the fall. If you'd like to TA for me in the spring, you should reach out to me. Hopefully the course will be a little bit smaller going forward in the future with lower late days queue times. That's the reason why we're moving to 2 of these things. If you're interested in this stuff and you haven't taken some of our other systems courses, there are a lot of really good systems courses where I suspect that you'll happen to have a lot of overlapping material in operating systems or distributing systems. And each of those fields is going to have a slightly different perspective on the same material. So even though you've seen locking and these kinds of things, you'll see it differently there. So it's totally worth taking. So those are some classes. And I wanted to always finish up with talking a little bit about, we do really stress classes a lot around here. And there's a lot of things to do at CMU that are not classes. And this course is a hard course. It's not a huge amount of work compared to some of our other courses. It's a lot of work, but it's not a huge amount of work. But I hope we try and make sure that everybody has the ability to do different things in this course. If you love programming, you can spend plenty of time programming. If you love doing your own stuff, this project is one of the first examples of taking on a big project. If you really like the algorithms and more some of the theory, you get to show that off on an exam. So we make the exams hard on purpose. We make the exams not count very much for the grade because we'd love to give people that are really good at that stuff the chance to shine, even though most of the course grade is depending on your homework assignments and your final projects. So that is by design. So I wanted to talk a little bit about the amazing CMU student and the ultimate good job. So how many people here are not about to graduate and locked in, and so that sort of have some decisions they can still make in life? Cool. All right. So this part of the talk might be a little bit for you. For those of you that are already locked in, this will be good for you whenever you decide to make a move at some later point in your career. So at CMU, I feel pretty strongly that this is sort of the path of many of us, is that you have this amazing CMU student. He or she works really hard to maximize their grades in classes like this class, in like 418. That high GPA looks really good on a resume. That good resume is very useful to hand out at the TOC, especially if you can talk about some of the projects in this course. I get students all the time saying, hey, I kind of just got an interview question that was exactly what we asked on the exam. And it's not by design, it just happens. Resume gets student good first round interview. Student knows his or her stuff in interview because they did put the work in these courses. ACE is the fine-grained linked list locking question on the whiteboard that Google happens to ask you, and you get a good job. Woot, right? So tuition pays itself back. In practice, the workflow is a little bit more like this, especially for those of you that are undergrads here, which is, you know what, I'm here. I don't want to just get a CS degree. I want to also get math. I also want to get EE. I also want to get a triple major in physics, which means I'm taking 6 hours, or I want to graduate in 3.5 years. There are good reasons for that, to be honest. And then you end up with, not sleeping at all, taking 6 courses a semester, having an even more impressive resume at the TOC, also gets you a first round interview, gets a good job. And the point of this slide is not meant to say that this is just as good as the other student. The point of the slide is that this is what many of you are doing. In fact, because it sort of takes doing this to get this good job, or at least it is perceived as that's the case. So the class discussion, as we make this a little bit more participatory, is why is this the path that everybody's following? People ask you, can I take your course? I'm like, I'm already, how many courses are you taking? You're taking 4. Really, you're going to add a 5th? Why are people doing this? And this is not I would like to have that discussion. We have 20 minutes. Yeah.
All of your smart, like all the people you perceive as like very smart are also doing that, and you want to be smart.
And you want to be smart. So in some ways, yeah, you're like, look, all the smartest people in high school took 7 AP classes. And they got, it's been a while for me. What's the score? Yeah, they got 5s on those AP classes. I couldn't remember if it was a 4 or 5. Maybe I got all like 4s, and maybe that's why. And so that means that the smartest people at CMU must be the people that are taking and getting A's in the most systems classes. That is the logic, and I'd like to claim that that may not be the optimal path to getting to the good job in the bottom right hand of the screen. So what I am not saying is that you should not be not sleeping at all, actually. Is that I am not saying that if you want to be really good at something and to get that good job, you do need to be really good at something. Absolutely. You do have to work really hard about it, and you do have to think about it all the time. And there are very, very few people that don't think about things all the time and are amazingly good at them. I happen to not be one of those people, and very few people are. Actually, those people are very, very lucky, the people that just pick up the pencil, walk into the exam, and nail it, right? I also want to point out that this is not the common, if you work really hard, you will be successful argument, because I don't believe in that. I say if you work really hard, you will get good. If you want to be successful, you probably have to be lucky as well. And we should keep that we should acknowledge that. So my hypothesis is that for some of you, not all of you, the path that I started this segment with is a perfectly reasonable path. But it is not the only way to spend your time here at CMU. For some of you, challenging yourself to ace as many classes as possible may not actually be the most effective way to maximize your time here at CMU, especially if you're an undergrad and you have a lot of time. It may not be the best way to get a competitive job. It may not be the way to get the coolest job. And it may very well not be the best way to prepare yourself to have the most impact when you do get a good future job. And there are other ways to demonstrate that you are one of the best students here. I'd like to talk a little bit about that. So one is I think that people should manage themselves more wisely in what classes they choose at CMU. And this is much easier said than done because it's absolutely true. Some of the best students are taking many good classes and doing an exceptionally good job at it. It's also very true that we have some excellent classes here, so it makes sense to want to take all of them. You learn a whole lot in them. But imagine this situation. Here's the situation I'd like to present. You are signed up for a normal load of 4 classes. Now, this may not apply to you anymore, but this may have applied to you last week or last semester. One of them is this class, SCORE. But you are considering loading up with distributed in the same semester. 4 classes versus 5, or 5 classes versus 6. Who's been faced with this decision to make at CMU at any point? Okay, what did you decide? Okay.
Some semesters I said I'm going to have an easy semester. I'm not going to take, well, in that case it was category theory. I said I'm not going to take category theory. Sounds like yeah. And then I took the semester, I'm like, this is a little easy. And the next semester I was like, I'm going to take, 4 CS classes and one of them is compilers. And, life happens and it's very difficult. So like...
Exactly, okay. So you have some options. There's a lot of, life has a lot of options. Those of you who already got a job, you're out of options. But just kidding. So you could do what it takes to get A's in those 5 classes. And many of you are probably doing that this semester. But if you're taking those 5 classes, you're going to be busy. So what if you gave reasonable effort in my class because you're like, look, this parallelism thing is, like earlier in the lecture, it's an important thing to know these days. But I don't see myself as someone doing this as my day job. I'd like to know about it. I'm really interested in distributed, or I'm really interested in category theory. You could decide to say, you know what? I'll do a reasonable job in Kayvon's class. I'll get a B, or I'll maybe get an A without trying to put much work in. But that will give you a lot of time to do an outstanding job on the final project in category theory. Right? So, in some ways, maybe I'm making this cliche argument of, look, you should always find ways to do the things that you're interested in, kind of blah, 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 right? Which, I actually kind of agree with you. You should find things to do time to do things you're good at. But if you spend a lot of time on the things that you are interested in or good at, if you take the 4 classes and do a bang-up job on that project, maybe taking it easy in my class or maybe not taking my class at all, that bang-up project is going to come up in a job interview. It's absolutely going to come up in a job interview. Because if you're interested in category theory and you go work at Google's category theory group, there will be a lot of competition for that group because it's probably a small one. No, just kidding. Sorry, Bob. They're going to say in an interview, oh, yeah, I saw you take that class. Tell me about your final project. And if your project is just, yeah, I did this. It was a pretty obvious thing to do. That's one thing. If your project is, I blew off all my other classes and did all this, I went deep into this project. Or, for example, the project in this class, that's going to really, really show up in a job interview. And the really unique opportunities, the really cool jobs at Google. I'm not saying jobs at Google is not a really cool job, but certain jobs at Google are cooler than others. You're going to get by knowing people. And you're really going to get those most of the time by knowing people. And so you better believe that our friends in industry are asking us all the time about certain students. And I have a lot of students in my class, right? It's easy for me to say, yeah, they got an A. It's easy for me to say, yeah, they did a good job on an exam. But if I remember your project, then what I say is very, very different to those people when they call me about something. Like, look, this person did a pretty amazing project. You should check it out. It's still on the web. That's what gets you a really interesting job. So continue along on this theme. Instead of taking that 5th class, there's always undergraduate research or an independent study. There's probably tons of things that you like doing. Let's go back to that student that was doing this triple major. They never sleeping at all, really impressive resume, did well in a bunch of classes, got a good job. Well, the person, there's a slightly different path, which is takes fewer classes, still doesn't sleep at all, but they're not sleeping at all because they're working on this amazing project in 418, right? Because they're really interested in getting a job at the distributed systems group at Facebook, and they want to make sure they can nail that interview, right? So they're really interested in parallel systems, right? And then that student says, hey, Kayvon, I liked your class. Is there anything I can help you with next semester in your research lab? And I'm like, oh yeah, that was that project on that really interesting load balancer. Like, I thought that was really good work, right? Like I remember that one. And I'll be like, yeah, dude, you did the coolest work in 418 in the last couple of years. Why don't you just come hang out with my PhD students and work on something? And then you get some awesome experience working side by side with PhD students on some project. You probably still don't get a lot of sleep. I'm not saying you're going to take it easy, but that's kind of how it goes. And then, maybe I hear through the grapevine that somebody's looking, and I'm like, hey, you've really got to talk to this guy because he's doing some bang up work. And it's not published. It's not published. He doesn't have any papers, but it's almost as good as that kind of stuff. And that's where the wicked cool jobs come out of. They might be at the exact same companies, but they're different jobs. And I'm saying this not because, in some sense, this happens every year with students, that do great projects. It also happened to me. I wasn't thinking about any of this stuff. I took a graphics class at CMU in 2012. A TA came up to me and was like, hey, that was a pretty cool project. You should come hang out with us in the lab. And I was like, I never thought about hanging out with you guys in the lab. Okay, sure, I'll come hang out in the lab, right? And I was really, I sort of leveled up once I started hanging out with the PhD students, right? And that's Kieran. He's actually looking for hire people these days. So, why research or why an independent study? Well, you will certainly learn way more about a small little topic than you ever would in that class. And if you can learn a whole lot about one topic, it's good evidence that you can learn a whole lot about other topics later once you get hired. So being deep is a good thing. And you think the people in this class, or you think those people taking 5 classes or 6 classes and getting A's are really smart. Imagine hanging out with some of our PhD students. Those people are also very, very smart. It's also just way more fun to be on the cutting edge of doing things that people don't really know the answer to. Now that's a personal preference, but some of you may agree. And I thought when I actually went into the lab, it really widened my perspective on what was possible in computer science. And one of the most valuable things you can have is have a broad perspective on seeing what's going on in the world and being able to understand those trends. And of course, maybe you might end up liking it and you may end up going to graduate school. And remember that comment about people, who you know, and I don't mean that in a smooshy way, it just means people that see you doing stuff are really excited to help you out. Without question, the only way, I say the number one way, basically the only really way to get into a PhD program in grad school is to have a professor here write a letter for you saying, this person was just doing some great work as an independent studier in my lab. That is the 90% of the metric of admissions. And so if you don't have that, you get what we often call a did well in class letter, which says this person did an amazingly good job in class, and that's all I know about them. And those tend to kind of get tossed pretty quickly. And that, I had a similar experience as I sort of ended up helping a professor my senior year. I had no clue what I was doing. I helped out with a paper. At some point I said, yeah, I'm not sure, I've got a few industry offers, but I do want to go to some form of grad school. I'm interested in going to a master's program. That's what I told my, and in this particular case, they told me, hey, you're doing a lot of research. A master's program in computer science is not usually about research. That's a PhD program. I didn't have a clue. And this was like the email, you can actually see it, is I said, hey, could you write me a letter? And they said, no, we are not writing you a letter to master's programs. We will only write you a letter if you apply to PhD programs. And so that's sort of how things got started, right? So I'm not making an argument for research, actually, here. Research is just one option. Many faculty around here will tell you that research is the best option, but that's because we're highly biased. I think that there are many much better options in some situations. So, why not start your own project, And there are many opportunities to do so here at CMU, right? We have Scotty Labs, we have Surge, we have Tartan Hacks. There are many places to take on an independent study or do something of your own thing, right? Like, you might like it enough, you say, you know what, I cannot stand having a boss. I can hardly stand having a professor. You know, I do not want a boss in my life. And maybe you go start your own thing, right? And that could be a very useful experience. And why go work for Zuck if you can have him buy you? So the point being is there are many, many ways to be excellent here at CMU, of which take more classes is one of those very good ways. But it's a different type of skill set that you will learn. You will be handed problems. You will get a lot of experience solving them. You will become good problem solvers. That's one way to do really well. But there are other ways that are less structured, and you get to pick the problems to work on. And sometimes picking those problems is actually harder than solving them. And that's a good experience too. So the problem with the bottom half of the slide is that things may not work out. Most of you, if you put your mind to it, you're going to get reasonably good grades in many of your classes here, if you put your mind to it and work hard. These things, you could work hard and be unlucky, and it may not work out. So, you know, getting comfortable with the fact that something may not work out is a very useful skill to learn while you are here. You know, when your mortgage doesn't depend on it working out. So there is a higher likelihood of failure on the things on the bottom of the slide, for sure. But I encourage you to try and take on some of those things, which may blow up in your face. This class is doing the final project in the way that it is for a reason. So getting over fear of temporary failures, the possibility that things may blow up in your face, is a very useful skill to learn now, because you don't learn this later most of the time in life. And in fact, you know, this is one of the things that I regret, is that I did not take enough risks when I was an undergrad, and I've been trying to overcome risk aversion in choosing projects and stuff ever since. So I'm not saying failure is good. Failure is not good. Failure is good if it causes you to grow so that you are successful at a later date, right? Like, this is not a keep failing, it's fine. You need to reevaluate things if it's, you know. Okay, yeah, so, and all of those things, you know, could very much blow up in your face. So in my perspective, it's not actually that you have nothing to lose if you're here at CMU. In fact, you actually are in a position to, you have more leverage. You have the position to take a few risks when you're here as an undergraduate or early master's student, because the cost of failure is significantly less for you than for other folks. Other folks sometimes have one shot at that Google interview. They've got one shot. If they mess it up, it's trouble, right? If it doesn't work out, if one of these risks doesn't work out, you've got it. Most of you have a really good fallback plan. I mean, you know, some people that's not true, unfortunately, for economic reasons. But for many of you, you have a really good fallback plan, and that's a job at Google, that's a job at Facebook, that's a job at those places. You know, that stuff's not going away. Okay, so the takeaway point is think a little bit bigger. You know, be a little bit more ambitious when you still have some time left here, right? You are very smart, you are very talented, you are fortunate, but also well-deserving to be in an environment like CMU, where there's a lot of great people around. Think about what everybody else is doing. How can you maximize that opportunity when you are here is something you should ask yourself, for example, over the summer. And I would say that the biggest sign that you've entered the real world is not that you're paying a mortgage, it's not that you're making your car payments, it's not that you dress nicer and eat at better restaurants. It's that you're actually able to take on and ask yourself questions about making your own decisions. Not just doing the problems that I give you, not just saying, look, I'll take your class, you take me on a ride all the time, but actually making some of your own decisions. So, final claim of the class is it is far more difficult to ace the final project, pick a good project and actually pull it off, than it is to get an A on my exam. It's pretty hard to get an A on my exam. It's a tough exam. But it's far more challenging to be able to pull off an amazing project. And that's also true, senior thesis, independent study, starting a company, starting your own club, whatever you want to do. And the world rewards people that can pull that stuff off because the world knows that it's way harder. So many people are really smart. Many people can work really hard. Far fewer people can pick good problems and succeed and take the leadership to pull them off. So that is my suggestion for what you should spend your time on over the next couple days. Thank you for being a great class. Hopefully some of you will hang out with us in the future as a TA or something like that. And see you a week from Monday.